want to just do this is all stuff you guys have done. So this is going to be pretty much a review. I want to zip through it though. Maybe there might be a couple things I can show you that might help you organize this process. We're just going to look at arithmetic with polynomials, specifically adding and subtracting polynomials and multiplying. Really not a big deal. Adding and subtracting could not be easier. It's really just a matter of collecting like terms. What are like terms? First of all, same variables, and they have to be good. The same. Well, the coefficients could be different, but the variables have to be the same and same exponents, right? The variables have to be to the same powers. So, for example, these are like terms. Here's examples of like terms because the variables are the same and each variable is to the same power. These are unlike terms because although they're the same variables, the exponents are different, right? So when we combine like terms, it's really just a matter of kind of going through the list and finding the ones that match up. So in this case, if we look for the x squared y, it looks like there's two x squared y. We just combine those. How many total would we have? 11. Looks like how many xy terms? And then how many y terms? There you go. Okay, give me thumbs. That all makes sense. No big deal. Okay. So when we add polynomials, it is literally just combining like terms. Subtracting polynomials is essentially the same thing. The only difference is when you're subtracting polynomials, you just need to distribute the negative sign and then combine them. That's it. Right? So when we add these two polynomials, what I would say that probably the best way to approach this would be you always want to try to eliminate grouping symbols and then combine like terms. Do you have to do anything to eliminate those parentheses here? No, I can just erase them, right? How come? How come I can just get rid of them? If you have nothing to distribute, I mean, what am I distributing here? What number? One. And distributing one doesn't do anything, right? Multiplying by one doesn't change anything. The groupings, the quantities aren't taken to any exponents, and there's nothing other than one out front. So we literally just eliminate the grouping symbols and combine like terms, right? So we just eliminate the parentheses and then combine like terms. And as we're doing this, we always want to write the polynomials in standard form, which means we're always going to kind of target the highest powers of x first and then just work our way down. And then if we do that, we automatically write our answer in standard form. Give me 1 to 5 minutes. That all making sense? And so here, what would I do? Distribute the negative. And what would that give me if I distribute the negative? 4 plus y plus 4. And then I just combine my terms and I'm done. How about this one? Quickly walk me through. First set of grouping symbols, do I have to do anything? Get rid of them. Second one, distribute the negative for the second quantity, and the third one, just erase it. Okay? So we end up with that. And then I just combine like terms. What would the first term in my, everybody look at that for a second. What would the first term in my polynomial be? 3a squared, great. If I add up all the a squared terms, I'm going to get 3 of them. What's the 3a squared? What's the next term going to be? Say it again. Minus 6a, because there's only one term. Good. And then plus 11 looks like, yeah. Okay, plus 11. Okay, good. One side, real good. No. Okay. All right, what about multiply? So, multiplying polynomials, we've already done stuff like this top example, right? This is really just properties of exponents. What do you do when we multiply monomials? What is a monomial? polynomial with how many terms? One term. Yeah, good. So I've just got a coefficient times the power of x. When I multiply monomials, we're going to take advantage of our properties of real numbers here, right? We're going to take advantage of the fact that multiplication is commutative and associative, so we can regroup these things and multiply in convenient order, right? It makes sense that we would want to multiply the coefficients first, right? So we're just, that's going to give us a negative 6, and then we're just going to go through and multiply through the various different exponents. Usually we've only got one of various different variables. Usually there's only one, typically x is. X squared times x is what? X squared times x is x cubed. And the reason for that is because when I multiply like bases, what do I do to the exponents? Yeah, good. Good. So we did 6x cubed. Now, if we had something where we had multiple variables, which, I mean, we're not going to deal with that a lot this year, but it's still a big deal. In this case, again, I've got monomials with multiple variables instead of just one. Again, you just group the numbers first. So 6 times negative would be my negative 6. Then we're going to multiply the x's. Well, there's only one x. Then we multiply the y. So y cubed times y to the 5th. That's y to the 8th. And then last, we'll just multiply the z's, right? So we multiply like bases. The base c squared times the base c to the 6th of that. Now, when we extend that, then we're not just multiplying monomials. What if we're multiplying a monomial times a polynomial? Well, you just distribute, and then each term, you're just going to use that same approach for multiplying each term together, right? We multiply the coefficients to get a number, and then we multiply the variables to get a power of the variable, right? Okay. So 1 to 5. Okay. And if we're multiplying two polynomials, then we're just going to do the same process, only we're just going to distribute all the terms from one polynomial to the other polynomial, and then ultimately collect like terms, right? So there's not much to this. You guys have done this, I mean, many, many times in the past, I'm sure, stuff like this. There's one strategic element here, though, that I think is worth mentioning. Now, in this case, it doesn't really matter which polynomial you're distributing from, right? It doesn't really make any difference because they're both trinomials. If, in my opinion, and you can do this either way, but in my opinion, when you have something like this, where you've got a binomial and a trinomial, I personally think it's easier to distribute from the smaller polynomial, one with fewer terms. So what I would suggest is you would take the two terms in the binomial and distribute those over the bigger polynomial. I think it's just easier to organize that way. Okay. All right, so let's just go through one of these here. What do I do? Okay, good. I'm going to distribute the 2x squared all the way through. So I'm going to do this, right? So 2x squared times x squared, everybody all together is 2x to the 4th. Good. 2x squared times 3x, everybody, 6x cubed. Okay. 2x squared times 4 is 8x squared. Good. What's next? Dx all x times x squared is, so I have an x cubed, x times 3x, so I have 3x squared, good, x times 4, 4x, so I have 4x. And then finally, I distribute the negative. Distributing negative 1 really just does what? It just flips the signs of the second polynomial, right? So I'm going to get negative x squared minus 3x minus 4. And then it's just a matter of collecting like terms. So this is the step, honestly, where I think if you're going to make a simple mistake, it's probably on this one, where you just forget one term when you're combining terms, string like this, I think what's not bad is just to go through and like underline them or check them or something as you go to make sure that you're accounting for all the terms. So what power of x should we start with? X to the fourth. Looks like there's only one x to the fourth term. 2x to the fourth. What's next? Show with your fingers how many x cubed terms are there? Two, it looks like. Okay. One there. One there. Total of how many x cubes? 7. Okay. How many x squared terms? Looks like 3. 1, 2, 3. Add those up for me. 8 plus 3, 10 minus 1. 8, 10 total. Yeah. Whoops. So x squared. It looks like there's 2x terms, 4x minus 3x. Just get a plus x. And then finally, at the end, I've got 1 minus 4. And then it's automatically, like, careful to go in descending order. It's in standard. Okay? All right. Why don't, oh, and I'm going to show you. Here's a trick that I think is helpful when you're multiplying big polynomials. Like especially, what if you had a trinomial times a 4 or 5 term polynomial? Then there's lots of distribution. It's really easy to get mixed up with collecting terms. So one thing you can do here is you can organize the terms that you get when you distribute into columns. Okay, so you know in advance here, you can already anticipate what's the degree of this polynomial going to be. Everybody show me your fingers. What's the degree of this polynomial going to be? What's the degree again? Remind me. Biggest power of the variable, yeah. Everybody agree it's going to be 3. You can already anticipate because the leading term times the leading term is going to give me the leading term of the resultant polynomial. So it's going to be a w cubed is going to be the biggest power. So then you just need to, you don't have to like write these column headers out, but in your mind, you're going to partition off columns for every power of the variable. And then when you do your distribution, you'll just place the products into those columns. And every time you have, like, so I'm going to get one row for each series of distributions. Like when I distribute the W, that gives me a row. When I distribute the -7, I get another row. If there were a third term, that would give me a third row. And it's really easy to add up the like terms in because they line up vertically. I think that's pretty handy. So for example, let's do this real quick. If I distribute the W, what do I get? W cubed plus 2W squared plus, good. If I distribute the -7, remember I distribute the negative, so what do I get? Okay, -7, good. And you get, and everything's lined up vertically, so it's easy. It's easy to add everything up. Okay, nothing so magical, but it's kind of a handy thing. Why don't you guys? Okay, now I'm gonna have you do one on the board here, just get you moving around. Let's before you do though, let's just take a second and let's talk about how are we going to proceed here with this. How many factors are being multiplied here? Show me with your fingers. Yeah, there's a total of 4 things being multiplied, right? Okay, now think about how we multiply multiple factors together. What's the process? You have to, okay, so but you have to do it in pairs, don't you? Like if I ask you to calculate real quick in your head, what's 2 times 3 times 4? What's the answer? 2 times 3 times 4. 24. Okay, you all get 24. How do you do it? Did you do it all at once? No, you did it in two, right? You multiply in pairs. 2 times 3 is 6. Multiply again, times 4 is 24. So my point is, you can't just do this all at once. You have to kind of do this, whittle away at this piece by piece, right? Now, part of being an advanced math student, you start to move into more and more advanced material every year. When you get up to something like calculus, things start to get complicated. Calculus, at least half of what we talk about is not how to do it, but how to do it efficiently. Because you can take really, really long journeys in calculus that take 20 pages of work, or if you're smart about it, you can turn that into less than a page of work, right? So it's always worth thinking. So the further you go in math, the more time you want to invest up front thinking about planning a pretty clear solution. This isn't such a big deal, but if we're looking at this problem, does anybody have any ideas about what might be the most efficient approach? What do you think? Yes. Okay, so one approach would be maybe to distribute the 3 to this first one, and then, okay, and then what do you do with that? Multiply by the next one, so on and so forth. Okay, that would work. What I typically do with these, if I have a coefficient out front, I typically don't distribute that until the very end because it makes the coefficients bigger then, and every time I multiply, I have to do a bunch of distributing. I've got to deal with bigger numbers that I'm distributing. Does that make sense? To me, it's I would prefer personally, like for example, to take these two, FOIL them out, simplify. I've got pretty small coefficients. Then I'll distribute this other polynomial, combine my terms and simplify. I've still got reasonably small coefficients to combine. And then when all that's done, one time I'll distribute the number out front. I only have to multiply big numbers one time. But what if that number out front were a third? Right? Then I've only got to distribute that big number once instead of repeating it every time. Does that make sense? Okay. All right. Why don't you guys go to the board? Work on this one. Just spend a second talk about this one. So what if we organize like this? What if we said we're going to multiply those together first, right? So that if I distribute the a, that's going to give me a squared plus 8a, distribute the -2, right? Okay. We want to definitely simplify that completely before we do any more distribution. We want to distributing is where things it gets kind of messy, right? So we want to minimize that. So we would combine these terms and just make that a squared plus 6a minus 16. And then I've still got these other factors out front that I haven't multiplied yet. Well, now we would maybe do that process, right? Distribute those. I distribute those. If I distribute the a, that's going to give me what? A cubed plus 6a squared minus 16a. If I distribute 5, I'm going to get plus 5a squared plus 30a minus 80. And if I combine all that stuff, I get a cubed plus 11a squared. See how nice it is that we stack those vertically? Plus 14a minus 80. And then finally we bring down that -3. And the last step would be to distribute that -3. And that gives us -3a cubed plus, minus 33a squared minus 2a plus 2a. Got it, right? Make sense? Okay, last thing I'll show you, and this isn't really a big deal. You also have the option, if you're multiplying polynomials, here's another way of doing it that kind of organizes the combination of like terms. If you multiply vertically, this is like when you back in the day when you guys first learned how to multiply multi-digit numbers, and you stacked them up vertically like this, right? Same rules. Instead of having places for the ones, tens, hundreds, and so on, now you just got places in the polynomial columns for each power of x. And just make sure you put the appropriate terms in the appropriate columns, right? So when I multiply the 9 all the way through, the results just go in the correct column. So 9 times 9, 9 times 5x, 5x. I'm adding these terms, right? And then 9 times 2x squared, 18x squared. I distribute the 7x. Again, I'm just careful to put the partial products in the correct columns, right, before I add them up. 7x times 9, 63x, 7x times 5x, 5x squared, 7x times 2x squared, 14x cubed. And it's easy to add those things up, right? So what do we get? Quickly do a little mental math for me here. 18 plus 35, 53. 3x squared, 45 plus 63. There you go. So it kind of keeps it organized too. Make sense? Okay. All right. Turn you loose. Let you guys work on this a little bit. Make sure that assignment's up. Tomorrow we'll go through some new stuff.